Hi, in this video we're going to look at how using logarithm transformations can allow us to find the equations of exponential and power functions. So lots of times when we graph data, looking at a different scale can help us identify a more appropriate model. So in this example I've got some data where my variables are related by an exponential growth model. So here I've got my actual equation is y equals 2 to the x. And when I plot my data points on the original, the natural axes, then I get a curve where my data has this exponential growth. It's a concave up and increasing function, and I can't use the equation of a line to find that. On the other hand, the second graph shows that I've changed my axes. This is an option in viewing a scatter plot. For example, in a spreadsheet, we can set it to a logarithmic scale. So here I've got my y values at a logarithmic scale. So here's 10 to the minus 1, or 0.1. Here's the location of 1. And here's 10 to the 1, which is 10. And so now I've plotted my values. So this value of 4 happens to be at this height of 4 in a logarithmic scale instead of a linear scale. And when I look at this exponential data in this logarithmic scale, it looks linear. And so that's the idea. We're going to be using a transformation of our axes so that the data becomes linear in the new scale. Here are the key facts we're going to work with. An exponential function, so that's where my dependent variable y is a constant, here it's a, times a base, that's also a constant, raised to the variable's power, x. Now if I look at that in a semi-log plot, so that means that our y-axis is in a logarithmic scale, that's where I get a linear plot. And that's what we saw in the previous example. The exponential function, when the y-axis became logarithmic, looked like a line. A power function, here where my dependent variable is a constant, again a, times the variable raised to a power that's a constant. If I look at that in a log-log plot, where both axes are transformed, that's when it looks linear. So mathematically what we're going to do is anytime I transform an axis, we're going to consider a new variable representing that transformed axis. So here if I have a semi-log plot, that means my y-axis is logarithmic scale. I'm going to be thinking about my second variable now as the logarithm of y. If I'm doing a log-log plot, then that means both axes have been transformed, and so my transformed data, I've taken a logarithm of both the x and the y values. And so what we're going to do is we're going to find these transformed variables and then find the equation of a line. And when I find that line, I can then solve for my dependent variable and put it in a standard form. So the examples that we'll look at following this are going to illustrate that principle. For our first example, we are going to find the equation of a power function that passes through 2 points. And so let's start by reminding ourselves of our model. Our model is that we have a power function. Y is a constant times the variable b raised to some power. And that's our model. That's the standard form that we want to find. Now what we're going to do is we have our original variables x and y, and I'm going to create a table as if I was creating a plot in a spreadsheet. So my first point was the point 2, 5, and my second point was the point 5, 10. And those are the values of my x and my y values. Now because this is a power function, what we would do is we would note that this power function would look linear in a log-log plot. So we're going to do a log-log transformation of our data. What that means is I'm going to create a new table that has log of x and log of y as my columns. And I prefer to think of logarithm as a function rather than just a related number. So I'm going to think of this as the log, this is base 10 of both x and y. So my first value is going to be log 2, and my second value is log 5. And those are the transformed coordinates that came from the point 2, 5. Similarly, the point 5, 10 is going to have a transformed independent variable of log 5 and a transformed y variable of log 10. And so these are the values that I would work with. Now if I was in a spreadsheet, I would actually have decimal values for that. Mathematically, we're going to leave it in this form so that we can have exact values. So this relationship is linear because it's a power function. It looks linear in a log-log plot. And so if I want to find the equation of a line, the equation of a line requires that I find the slope and a point. And so we're going to use this first value as my point, but I do need to find my slope. So the slope is the change in the output variable, which for us is the log y, and we divide it by the change in the input, and for us that was log x. Now the reason I'm not saying delta y and delta x is I'm working with my transformed variables. So when I find the slope, the change in the log of y, I'm going to subtract the values log of 10 minus log of 5. And when I do my change in log x, I'm going to take the log of 5 and subtract the log of 2. So our first point, our change in y, is log of 10 minus log of 5. We're going to divide that by the log of 5 minus the log of 2. Now, usually when I'm doing this, what we're going to be doing is we're going to be applying the properties of logarithms. And so the property that we're using immediately is, I notice that I've got a logarithm minus another logarithm. And so it's important that we recall what that rule was. If I have a logarithm of any number and I subtract the logarithm of another number, the rule was that that's the logarithm of the quotient. And so when I apply that, I get that my slope is the logarithm. Here is log 10 minus log 5, so that'll be logarithm of 10 divided by 5. And on the denominator is the logarithm of 5 divided by 2. Which we could simplify. 10 over 5, that's 2. So log of 2 over the log of 5 halves. I'll leave it that way, but I could have written 2.5. That's my slope. And so I've got a point and a slope, and I'm going to use the equation of a line. So the point slope formula for a line with a slope m and a point a, b in normal variables would be y minus b equals the slope times x minus a. But for us, my variables are not x and y, they're log y and log x. So my equation is going to be log of y, that's my y variable, and I'm going to subtract the y coordinate of my point. So here it's log of 5. So log of 5. And this is going to be equal to the slope, which was log of 2 divided by the log of 5 halves. I'm going to multiply that by the log of x, that's my x variable, minus the point log of x, which was 2. Now, notice what we get to do again. I'm going to use the rule of logarithms, the logarithm of a difference in two locations. Okay. So, I get the logarithm of y over 5. is going to be equal to this slope, log of 2 over log of 5/2, just a number, times the logarithm of x divided by 2. And now we're going to use another property of logarithms, that if I've got a number times the logarithm of any other number, that the product becomes the logarithm of my value inside the logarithm raised to the power of the number on the outside. And so I'm going to take this number that we found from the slope, and I'm going to solve for, I'm going to put it inside the logarithm. So I get, the logarithm of y over 5 is now equal to the logarithm of the quantity x over 2 raised to this power. Be nice if we had a simple way of writing that. We'll just keep it like this. And now that I have the logarithm of one quantity equals the logarithm of another quantity, I can eliminate the logarithms by, these are 1 to 1, so I get y over 5 is the quantity x over 2 raised to the power, I should have just given it a name, let's call that p. P is this slope that we found. And if I want to solve for y, I'll multiply by 5 and get x to that power divided by 2 to the power, and I now recognize a power function. My y is equal to 5 over 2 to the p, where p is that ratio, times x to the same power. And I've got my power function. For my second example, we're going to look at what would happen if I looked at a data in a spreadsheet and plotted my data. Here, let's see what I have. I've got my x is a variable m, and my y is a logarithm of t. Okay, so what that meant was, originally I had some data, m and t, and I had some numbers here, and I don't know what they are. And when I plotted it, when it went to a semi-log plot, so here I've got my t-axis and my x-axis, m, I've got a standard axis on this value. That's because m was not changed, and I've got a logarithmic axis on my t. And when I did that, my data looked approximately linear. Okay? And so then, to find out what the equation of that line was, I used my spreadsheet and I created new columns. So I created an m and a logarithm of my variable t. And so I had the same values here, and then I had the logarithm of the first value and the logarithm of the second value until I filled in that column. And again, I plot this, except this time my axes are no longer the original variables. They're log of t and m. And I say, okay, I plot the data, and I get the same looking graph as the logarithmic scale, and it's still linear because this actually is a linear, approximately, a linear relationship. And when I ask the spreadsheet to tell me the equation of that regression line, that's when it gives me this equation. It says y equals, what is it, 0.314 x minus 0.277, except that the spreadsheet doesn't know that my actual variables are not x and y. So that's the first step for me. I'm going to write down the equation using my transformed variables. My y variable was the logarithm of t. And so that's equal to 0.314 times my x variable, which is m. If it was a log-log plot, I would have used log m here. And then I'm going to subtract 277. Okay. Now what I want to do is I want to solve for my variable t. And it's inside of a logarithm. And so I need to use the inverse function. And the inverse of a logarithm, I can write this, the inverse is an exponential base 10. So the log base 10 inverse is the exponential base 10. What that means is I'm going to take 10 raised to the power of each side of the equation, 0.314m minus 0.277, that's all in my power, and because they're inverses, on the left-hand side, 10 to the logarithm of t is just t. And what I need to do to finish is I need to write this in a standard form. Okay. What we're going to do is we're going to apply properties of powers. So here, if I look at my formula, I've got 10 raised to a power that's an expression. And the operation in this expression is subtraction. So what's the rule? If I have 10 raised to a power minus a power, the rule of exponents says that's 10 raised to the a power divided by 10 raised to the b power. Which means I've got 10 to the 0.314m divided by 10 to the 0.277. Okay. Alright, so then I want to continue. And now what do I have? I've got 10 raised to a product. So I want to think again. What's the rule? If I have 10 raised to a product, the rule of powers tells me that that's 10 raised to one power and then raised to the other power. So I've got 10 raised to the 0.314 power raised to the variable power m, and I still have on the denominator 10 to the 0.277. Okay. Well, I'm almost there. The last thing I want to do to put it in standard form is recognize that dividing by a number is the same as multiplying by a number. So it's 1 over 0.277, that's a number, times the number 10 to the 0.314 to the m. And so notice we're now in the form of an exponential function, a number times a number raised to the variable power. And if I wanted to get a decimal value for those, I would just plug them into my calculator. 1 divided by 10 to the power 0.277 is equal to 0.5284 approximately. So we should say approximately equal. And 10 raised to the 0.314 power is 2.0606 approximately raised to the m. And so here is my approximation of the exponential model that came from that log-log plot. So I just want to end by summarizing. If I start with an equation, log y equals ax plus b, so this would be a semi-log plot that I found a regression for. If I put it in this form, it always transforms to an exponential equation of the form 10 raised to the y-intercept b times 10 to the slope power raised to the x. And that gives me my exponential equation. If I do a log-log plot, so I've got log of y and log of x as my variables, and if that looks linear, so I've got a slope a and a y-intercept b, using the properties of logarithms and powers, it always will transform to y equals 10 to the power of the y-intercept times x to the power of the slope. And this is always going to work. And so you don't always have to derive it. If you have access to or can remember these formulas, you're able to quickly write down the equation of a power function and an exponential function directly from knowing the slope and the y-intercept of the transformed graph. Well, I hope that was helpful. Good luck.